We have seen that the rule of de L'Hopital provides a way to evaluate limits that are indeterminate of the form 0 over 0 or infinity over infinity. But in fact we can apply the rule to limits that are not formally quotients of the type 0 over 0 or infinity over infinity, but other kinds of indeterminate forms. For instance, we can have indeterminate products. So if a function f approaches a as x is approaching a, and g approaches infinity as x is approaching a, then let's take a look at the kind of situation we may have for the product f times g. So we could have, for instance, f is 1 over x going to 0 at infinity, g could be x going to infinity at infinity, and then the product of f times g at infinity is x multiplied by 1 over x, so it's a constant function 1, and the limit at infinity is 1. So when I multiply a function going to 0 by a function going to infinity, I could get, for instance, 1, so some constant. I could also get infinity, because we could keep the same situation for f. F is 1 over x and goes to 0 at infinity. And for g, let's take x squared, which of course goes to infinity. When we multiply f and g, we get x squared times 1 over x. That's x, and its limit at infinity is infinity. We could also get 0. Let's now consider for f the function 1 over x squared at infinity. It goes to 0. And for g, the function x, which goes to infinity at infinity. Then the product f times g is x divided by x squared, in other words 1 over x, which goes to 0 at infinity. So you see that we cannot conclude anything about the limit of the product just from the knowledge that the limit of f is 0 and the limit of g is infinity. In other words, if the limit of f is 0 and the limit of g is infinity, we have an indeterminate form of the type 0 times infinity. So how do we deal with it? The rule of de L'Hopital is dealing with quotient, not products. However, really, products and quotients are two ways to write the same thing. Specifically, we can rewrite the product f times g as f divided by the reciprocal of g, or g divided by the reciprocal of f. These are just three ways to write the same thing. In the left-hand side, we have this indeterminate product, 0 times infinity. The middle term is really an indeterminate quotient of the form 0 over 0, and the last one, an indeterminate quotient of the form infinity over infinity. And for the last two forms, really, we can apply the rule of de L'Hopital. And this is exactly what we're going to do to deal with indeterminate products. Rewrite them as an indeterminate quotient and apply the rule of de L'Hopital. So let's take a look at examples. Let's say, for instance, we want to find the limit as x is approaching 0 from the right of x multiplied by ln of x. X is approaching 0, ln of x at 0 from the right is approaching negative infinity, so we have an indeterminate form of the type 0 times infinity. But we can rewrite the products x times ln of x as ln of x divided by 1 over x. Now what we have is an indeterminate form of the type infinity over infinity, and we can apply the rule of de L'Hopital to the effect that the limit is the same as the limit of the quotient of the derivatives. Derivative of ln of x is 1 over x, derivative of 1 over x is negative 1 over x squared. We can rewrite this quotient as negative x squared over x, which is really just negative x. And the limit of negative x at 0 is 0, therefore our limit is 0. In the second example, we're looking at the limit at negative infinity of x squared multiplied by e to the x. X squared goes to positive infinity, e to the x, if x goes to negative infinity, e to the x goes to 0. So we have an indeterminate form of the type infinity times 0. Again, we're going to rewrite that as a quotient in order to be able to apply the rule of de L'Hopital. E to the x multiplying by e to the x is like dividing by 1 over e to the x, and 1 over e to the x is really e to the negative x. So one way to rewrite that is a limit at negative infinity of x squared divided by e to the negative x. Now, if x goes to negative infinity, negative x goes to positive infinity, and e to the negative x goes to infinity. Therefore, now we have an indeterminate form of the type infinity over infinity, and we can use the rule of de L'Hopital, stating that the limit is the same as the limit of the quotient of the derivatives. So it's a limit of 2x over the derivative of e to the negative x, which is negative e to the negative x. Now again, if we look at the limit of the top and the top goes to infinity, the bottom goes to negative infinity, and so we have again an indeterminate form of the type infinity over infinity. That means we can apply the rule of de L'Hopital to that limit again. And so it's the same limit as the limit of the quotient of the derivatives. Derivative of the top this time is 2, derivative of the bottom is e to the negative x. As x goes to negative infinity, the bottom goes to infinity, so we have something of the form 2 divided by something going to infinity, and the limit is 0. For the third example, we're looking for the limit at 0 from the right of the product of sine x with ln of x. When x is approaching 0, sine x is approaching 0, and ln of x is approaching negative infinity at 0 from the right. So we have an indeterminate form of the type 0 times infinity. We're going to rewrite that as a quotient in order to be able to use the rule of de L'Hopital. So sine x times ln of x, I can write that as ln of x divided by the reciprocal of sine x, which can be written cosecant x. When x is approaching 0, the top is going to negative infinity, and cosecant x is 1 over sine x, where sine x goes to 0, so it goes to infinity as well. In other words, we have an indeterminate form of the type infinity over infinity, and therefore we can apply the rule of de L'Hopital to the effect that the limit is the same as the limit of the quotient of the derivatives. The derivative of the top is 1 over x. The derivative of cosecant x can be written negative cosine x times cosecant square x. So now if we plug x equals 0 in this, well, let me rewrite this in a more palatable fashion to start with. The 1 over x, we can have the x at the bottom. When we have cosecant square x at the bottom, it's really 1 over sine square that we have at the bottom, so it's like having sine square at the top. So we can rewrite all that as negative sine square x divided by x cosine x. If I plug x equals 0 in this, at the top I have sine 0, which is 0. At the bottom I have 0 times cosine 0. Cosine 0 is 1. So 0 times 1 is 0. In other words, top and bottom both go to 0. So I have an indeterminate form of the type 0 over 0. But that means we can apply the rule of de L'Hopital to that. And so the limit is the same as the limit of the quotient of the derivatives. The derivative of the top, I have the square of a function, so I use the quotient rule. I obtain 2 sine x times derivative of sine x, in other words 2 sine x cosine x. And at the bottom, the derivative of x cosine x, it's a product, so I use the product rule. I get 1 times cosine x plus x times derivative of cosine x, which is negative sine x. So if we plug 0 in this, at the top I have 2 times 0 times 1, so just 0. And at the bottom I have cosine 0, which is 1, minus 0. So I get 0 over 1, in other words, 0.